Okay. Well, it's great to be here. I must say, I always enjoy visiting Sweden. It's been very rewarding. And I can tell you that the summer is even nicer than the winter. So thanks to the organizers for organizing this Strings Conference in Sweden for the first time. And I was asked to give opening remarks. And I agreed before I thought of anything to say, but I thought I had a long plane trip, so I would have enough time to prepare a good talk. Unfortunately, I fell asleep. So the talk, as you will see, is somewhat sketchy, which is just as well. This way I'll keep within my allotted time period. In such opening talks, before anything new has been said, what you're supposed to do, aside from giving a amusing beginning to a long week of lectures, is say some remarks about the general state of affairs. And I've done this in the past. I must say, thinking about it on the plane, it was not easy to answer this question where we now stand in string theory. What I will do is go through a bunch of current questions and issues that are being studied and try to say a few words about where we stand. But I think, to some extent, it's hard to be very clear at this point in the long history of string theory. It is very sobering to remind ourselves that string theory is 43 years old this year. And although extremely healthy, somewhat unclear as to whether we're still at the end of the beginning of the string theory or the beginning of the end of the journey we've embarked on. Last time I gave opening talk at a strings conference was in Rome 2 years ago, and I started with going through the list of questions that I asked in the opening of what is perhaps the first strings conference at the ITP back in 1985, 26 years ago. And I'm not going to go through that list. I'll just remind you of the kinds of questions that we were asking then, and many are still asking. For example, what is the nature of high-energy physics, high-energy scattering in string theory, energy is above the Planck scale, what picks the correct vacuum, etc. Can we test string theory in a qualitative, distinctive way? But then I asked some new questions that are the subject of current investigation: emergent space-time, quantum cosmology, life in de Sitter space, and of course, what are we going to learn? What will we learn from the LHC? And finally, question number one back then and still today is, what is string theory? So all these questions, although many of them we understand a lot more than we did 26 years ago, many of them are still at the forefront of current research. And there are even newer questions. The last question, of course, question number 11, in a sense, is the most important. The LHC we've been waiting for almost 26 years, and finally it is here and it is running, and we're still awaiting results. Now that, of course, is unfair because the LHC is producing results, billions of collisions, inverse femtobarns of data. They've rediscovered the standard model in a remarkable, precise fashion. The experimenters are doing a fantastic job. The machine is performing magnificently, but we're still awaiting surprising results. So far, there have been no surprises after about a year of serious running, and that is a problem. So far, the standard model is perfect. There are rumors and anomalies, both at the Tevatron and at LHC. The LHC, they don't seem to bubble up to the surface, but so far, the standard model works beautifully. Those of us who had something to do with the standard model, of course, can be very proud. It is an incredibly precise description of all the physics that we can measure, even now in the TV regime. But, of course, that paradox, as is always the case in science, that success depresses us. And we are still awaiting surprising results. Some people are very pessimistic and are worried that the lack of, say, the discovery of supersymmetry by now is a big problem. Should we worry? Well, I think everyone will agree that it's too early to worry, but that worry concerns us all. The point of view of string theory, unfortunately, it's not a serious worry, because it's not as if we have a standard paradigm that we could compare with what the new discoveries at the LHC. The worry, however, is that we will not discover supersymmetry at the LHC, and we will not discover anything new that would give us clues that could guide us to answer some of those questions that we've been unable to answer for 26 or more years. So this is a concern. I personally am not yet worried. We're just getting into the interesting regime. But I think we would have been a lot more excited here and elsewhere if there had already been if some of the beautiful experiments, results from the LHC had been surprising. As I said, for string theory, that is not a serious problem in the sense that we still lack a predictive model of beyond standard model physics. I mean, there are a lot of superstring motivated phenomenological models of beyond standard model physics, but it is fair to say that there's no definitive test that we can confront with the LHC, except for the feeling that it would be awfully nice for string theory if supersymmetry showed up at low energies. this poster, this rather beautiful poster that was the Strings 2011 poster. I'm not sure what the artistic motivation was, but I took it to be a sort of a description of some kind of internal Calabi-Yau compactification with handles and cycles and an illustrative string theory vacuum. But among all the so-called vacua that one can construct by increasingly clever techniques, there's none that really provides a predictive test of the theory at the LHC. So although we can't test string theory at the LHC, we still expect to confirm one of its major features, namely supersymmetry, and, as I remarked before, to get some new clues that we can't precisely say what they will be, but we're desperate for clues from nature that might provide, in addition to the mathematical structures that have been providing us with tools, give us some direction to answer some of those questions. Anyway, within the last year or so, as has been the case now for many years, string theory continues to be vibrant and exciting and to make enormous progress in a variety of areas. ADS-CFT and its implications, its tools, the tools that it provides, its the clues that it gives us, continues to dominate the scene. And there have been, and we will hear, and I'm here mainly to learn about the advances in the last year in integrable models and their connections to gauge theories and to string theory in 2 and 3 and 4 dimensions. The growing use of ADS-CFT to teach us about quantum critical points in 3 and 4 dimensions, superconductors, from originally quark-gluon liquid to now superconductors. This is wonderful stuff and has the great advantage of connecting string theory and string theorists to other vibrant areas of theoretical physics. There are some very interesting expansions or extensions of ideas of holography and duality between gravity theories and quantum field theories, which connect not to string theory with its enormous number of degrees of freedom, but rather to higher spin gravity theories, Vasiliev type theories of higher spin gravity in ADS space, to large n limits of theories like vector models or coset models, which appear to be dual to these higher spin gravity theories. So the gauge gravity duality appears to be even broader than that originally discovered for matrix models for gauge, for Yang-Mills theories. And finally, there have been absolutely remarkable, stupendous progress in our ability to calculate and understand the structure of the most perfect of all quantum field theories, it appears, the maximally symmetric supersymmetric Yang-Mills theory that is dual to AdS5 cross S5, string theory, and in the planar approximation. We've been having at the KITP a workshop on this for the last few months, led by Zvi Bern and Nima and others. So I've been exposed to an enormous amount. The name of the workshop has been The Harmony of Scattering Amplitudes. And it is truly a remarkable achievement that we are now able to calculate and analytically solve so much of large N supersymmetric Yang-Mills theory. Originally for the dimensions, the anomalous dimensions of the gauge invariant operators, then for some special Wilson loops, and now for gluon scattering amplitudes to all orders with any number of legs. It appears that one is close to having an explicit, at least prescription, for writing down the complete answer to many of these, perhaps pretty soon all of the content of the large N gauge theory. The mathematical structures that have come up in the course of solving large N gauge theory are extraordinarily beautiful, and they're formulated in they give a different way of looking at space-time processes in gauge theories, and perhaps in string theory, and they have suggested to some that there is some underlying structure that is perhaps located not in space-time, but in twistor space or in the Grassmannian, and is the kind of mathematical clue that might teach us how to address some of the profound questions like what is string theory or what is supersymmetric gauge theory, which is dual to certain corners of string theory. This might be the case. The structures are extremely interesting and powerful and provocative and new, but it also might be the case that this is just a result of supersymmetric Yang-Mills theory being a particularly beautiful integrable system for large N. And sometimes such systems have beautiful underlying mathematical structures beneath them which have no great physical significance or generalization. But in any case, it's a clue certainly worth following, and this field and its development has enormous power and is even useful indirectly or directly in calculating QCD backgrounds. Another exciting development, but somewhat vague, is that the point of view that Eric Verlinde has stressed recently in a very forceful way of trying to take very seriously the idea that space and therefore gravity emerge by integrating out fast degrees of freedom, or as he originally put it, interpreting gravity as an entropic force. This is, I must say, the the kind of effort that I find enormously interesting, because it is a very ambitious attempt to come to grips with what we all believe and say and have for years, that space-time is not fundamental, should emerge from something. And of course, gravity, being the dynamics of space-time, should do so in the same way. But what Eric has done is try to explore an extreme version of that point of view and deduce some consequences. The general path is that is suggested or exhibited by matrix theory or ADS-CFT, where we sort of know how space-time emerges, although the details of that are the subject of some very interesting recent work of trying to reconstruct the bulk theory and observables and answer interesting questions about, say, black holes, explicitly using the tools of ADS-CFT. But we sort of understand the emergence of space and gravity in these cases. So it is not clear to me yet whether Verlinde's ideas have a context in which they're more general. What he seems to be doing is trying to take those lessons and apply them in situations where one has no particular idea about what the underlying fundamental degrees of freedom, say, are. I think we're going to hear from Eric later at the end of this conference about an application of this to de Sitter space, where he seems to be arguing that the dark energy and dark matter emerge in this way simply as a consequence of having a heat bath of whatever fundamental degrees of freedom there are. Anyway, I find this very intriguing to try to push and take very seriously this idea of emergence that just about everybody in string theory agrees with, but which we're really totally unsure of what it means in a general context where we don't have a specific, well-defined duality that we can use to formulate the idea. De Sitter space, where we seem to live, unfortunately, poses so many important questions that have been now around for quite a while, and most of which are unanswered. We'll hear some of that here, I hope to learn. De Sitter space seems to be very difficult to treat even as a background space with quantized degrees of freedom. There are potential instabilities in perturbation theory. It is hard to know what the observables are. It is hard to know what questions to ask in a rigorous, well-defined way about de Sitter space. It's hard to know what holography could mean. It seems to involve screens or dual descriptions at time-like infinity. De Sitter space is a very difficult place where we happen to live. So here there are many, many questions and talks in this conference. But we seem to be coming back and back again to ask these questions, and the answers are still, to me at least, quite mysterious. So there are questions and there are questions and there are questions. It never seems to end. There were questions 26 years ago. Many of them are still here. There are new questions now. The newest and most difficult questions, in my mind, have to do with the emergence of space-time and with life in de Sitter space. Now, I like questions, and I like to say, when I give popular lectures, to explain to general audiences that questions are the essence of physics, of science in general. We thrive on questions. I say that the most important product of knowledge is ignorance. The more we learn, as we have been learning an extraordinary amount for 43 years in string theory, the more questions we know how to formulate, and that's what keeps the science going. But eventually those questions are answered, and I must say, after 43 years of string theory, it would be nice to have some answers. I hope to hear some of them at this conference. So that's all I really have to say. Or en stor conferens. Thank you.
So that's a presentation of a lot of questions. Are there additional questions?
Where's the coffee?